259 is given already to you. Is that correct? So profile is there, and find the value of load based on American Institute of Steel Construction code, which we are going to discuss this today, is understood. Yes, so it's very simple code. It is in your handout. I don't know whether you guys noticed or not. When I gave you the 3 or 4 sample final, at the end, there were 2 pages which were formula sheet, yes or no? In that formula sheet, the code is there, everybody, which I'm going to discuss this today as well. Is that understood? Yes?
Is that the formula sheet we can bring to class?
What?
Is that the formula sheet we can bring to class?
No, you don't bring it. You get used to it, but don't bring it. I give you because I don't want anybody write anything on top of that, so I give you a fresh one in class, okay? But you have to get used to it to know what is in it and what is not. So I put it there in order for you to use it. Is that correct? Yes, get used to that, what is on it, where everything is. So there are on the sheet, then including the column. Actually, half of those formula sheet is about the column, as it's about the energy, because those are the ones that you are going to forget. Is that correct or not? Yes? The rest of them, beginning of ME 218, everybody remember that. Is that correct? And also, there are formula sheet for the Morse circuit, for stress, and for strain and other one. Everything you want to know is there. Let's put it this way. Everything that you have to use. Formula is not, remembering is out. So it is all about how to use the concept for each problem. Yes or no? Now, what we did last time, so please remember that we went very quickly because of lack of time. Really, this quarter, I had one less day to teach. Therefore, I'm about 1.5 hours behind, or 1 hour, 15 minutes. And then we were a little bit slow, part my fault, part your fault, so let's put it this way. And then I need another half an hour or 45 minutes to do a couple of examples. In the other class, actually, I ran out of time totally, which I could not do a practice on the code. I did briefly, so I'm going to skip one of the earlier examples. Hopefully, I get to the code, at least get an example for you done. So this is this way. So now, what we did last time is this, that we said either the load is centric or a load is eccentric. In both cases, P critical end up finally to be equal to pi square E divided by LE over R square. Everybody have to understand that the key for an entire buckling depends on LE over R, which is called? Well, you are very slender, so you should know the slenderness ratio. That's what it is. Yes, slender. If you are very tall, but you are very narrow, there you look much more slender than me. Is that correct or not? So therefore, it all depends on the height, and it depends on the cross section together. So a very long column and very heavy column doesn't look as slender. Everybody understand what I'm saying? If the cross section, that R is representation of the cross section, which is I. Is that correct or not? L is the representation of length, and E is boundary condition. Yes or no? So we have seen this problem. I hope you have done some of your homework. I know a few of you came to the office hours and we discussed that. There are problems like this that I'm going to go over that simply just for you to realize what we were doing is like that. There was a problem I gave you. It is in the book like this. Is that correct or not? It is fixed and free on top. Yes, so it's sideways. When you look at it, it looks like this. This is the sideways from one side. Let's say from this side you are looking at. Obviously, this column, when you look from top, it has an x-axis and it has a y or z-axis, whatever you want to call it, because in the book, when they show the cross-section, they show it x and y. Everybody understand that. For us, it will be x and z. Doesn't matter. Is that correct or not? This column, if it is fixed and it is free, so please write it down. If it is fixed and free, obviously, it is going to buckle about which axis? Y, obviously, because Iy is much less than Ix. Is that understood? Because this is part of a static, at least. Everybody knows that Ix is much larger than Iy. So if this is fixed, this is top on both directions, it's never going to buckle about the x-axis. It's going to buckle about the y-axis. This is obvious for any object. This thing is not going to buckle this way. It's going to buckle this way. Is that correct or not? Which is about the weakest axis here. This is the cross section. Or this item, this is the same thing. It's never going to, sorry. This is not going to buckle this way. Is that correct? It's going to buckle this way, yes or no? Which is about the what? The panel on the door or the windows there. This panel never buckles this way. Is that correct? It always buckles that way, yes or? Which is about that axis, yes or no? Yes, which is the weak axis there. So therefore, in order to utilize this one, I don't need to support it this way. I need to support it that way, yes or no? So if I support here at the middle, I put here, let's say some fixed support like that, put here a little metal and connect it to something fixed to the wall. I do not let it rotate. Is that correct or not? Yes? Then become what? From this way buckling, I have L equal to, give me a number. Let's say L equal to 16 meters. Is that correct or not? Yes? So it buckles fixed free about the x-axis this way toward us. Is that correct or not? With the length of how much? 16 meters. But that's not going to happen if there is no other support. It buckles about the y-axis. We know that. However, since this is weak, I'm going to support it. Now we can put it both sides or one side. Then what happened here? If this is now 8 meters and 8 meters, this 8 meters is fixed and fixed. This 8 meters is what? 8 and free, yes or no? Because I'm supporting it like that. I do not let it rotate. Is that correct or not? Therefore, which way is going to buckle? I don't know. This has effective length of, it has a length of 8, but it is fixed and free, which has a K factor of 2. Everybody understand that. This is fixed, never happened because this is more critical than that one. So you consider this versus the other one because still you don't know whether this buckle first or this buckle because this has the length of 16 and the other one has a length of 8 and they have different K factor. Everybody understands. So you have to see what you have there, any item which is weak in one side and strong on the other side, this is the bottom line. You are going to support it in the weak side, yes or no? Behind every panel of this door, everybody sees that. If you open the door, somebody said even in the construction, in the wood construction, I saw in the wall, this is the column, this is the column. Now I saw this. What is this for? This is not carrying anything. You know what that's carrying? What is doing that? Bracing that's what you were saying, bracing the column in order to prevent that from the buckling, that we are effectively reducing the length, L effective. Is that correct? So that is the bottom line. That's what I used several examples last time to show you how that works. Is that correct or not? Then we went to eccentric loading. The eccentric loading, the formula become much more sophisticated as we go along. So let's do example. Remember what happened in eccentric loading? Your differential equation were different. Your formula were different. You don't have to worry about the formula. You have to worry about 3 equations, which is given in the handout. Those 3 equations are the following. First, for eccentric loading, P critical is the same. So please write it down. This is the result. Eccentric loading. P critical is exactly like centric, so it does not make any difference. The only difference is you have a Y max. That Y max for the one that we were studying, which was pin, Y max was like that. This was Y max, and P was here, and this was E. Is that correct or not? Yes, because that makes it eccentric loading, correct? And this is that. Then Y max was given with that formula. Y max is here because this is a sort of a parabola, and Y max is the middle based on this because this becomes an M, and M causes this to go like that. Is that correct or not? Therefore, Y max end up to be E multiplied by, what did we have there? So go back again, look at the formula there. Was equal to pi over 2, whatever. I don't want to put any mistake there, but you have it there in your notes. So let's go back again. Just put it there. What was? So E, we had E here multiplied by secant of pi over 2. The pi over 2 was out of bracket. This is one of the 4 P critical minus 1. So, but be careful here. this is into the bracket of secant. In the book, this is not there. That's one student brought it to my attention. So therefore, please be careful what you are writing there. Y max was given with this formula, which was, I don't know, formula 1028 or whatever it was there. It is in your book. So Y max is given with that. Pi over 2, P over P critical minus. There is two versions of it. One is P over P critical, the other one P over EI, because we can change P critical to that one and bring L over RE into the system. Both is the same, pi disappear. So notice if I put this P critical here, this changes a little bit. So they gave two versions of that. I think 1026, 1028, I don't remember the number. You can check it. Both Y max is given. And then when you want to calculate sigma max, the sigma max was equal to, obviously, it is this scenario. It's P over A plus MC over I. Yes or no? Because this is not centric. In centric, it was very simple. In centric, you calculate P critical with that equation. The sigma critical is P over A. Here, you have a bending, so you have a stresses due to the bending, which is MC over I. And then you have a stresses due to the P over A, and the two together may go through the buckling. Is that correct or not? Therefore, as you see there, there is this formula is still valid because this is the eccentric loading stress. Is that correct or not? Yes. However, M here is equal to what? M generally, if there was no buckling, M always what? P times E. Is that correct or not? How here, M is equal to P times what? Look, we are at this point where the stresses are maximum. So P equal to what? E times E plus Y max. And this is Y max. That's the problem. P equal to E plus Y max. That's right. So what happened here when I put this Y max here into that one, then we got that large equation, which we call it second formula. I show you on the screen. Is that correct or not? Which was equation 1038. Look at it. It's there in the handout I gave you. Look at second formula. I don't want to go through that again. This is the second formula. Is that correct or not? Equation 1035 and 1036. Is that correct or not? Yes? Let's now use them. Now, if we want to use this problem as an example, so this is Y max. Again, this one, when I put this here, this sigma max become secant or formula. Maybe I should put that one here somewhere that you can see. So for one more time, okay, the secant formula is the following formula. So let me write that one down. So sigma max is equal to P over A. There is, again, two versions of it. 35, there are two different forms of it, both the same, of course. 1 plus EC over R squared multiplied by secant of P over EI, and then multiplied by L over 2, and then the whole thing, that bracket, I mean the square root ends there, times L over 2, which we call it second formula. The problem with this one at the end of the class I mentioned is this. If I give you P and you are calculating sigma max, it is simple to do. Is that correct or not? But if I give you sigma max and I ask you calculate P, you cannot solve that equation. Because how can you solve an equation which has 1 over cosine and has P over A? Everybody understand that? It's not solvable except by trial and error or by graph. And that's why I gave you the graph. Is that correct or not? Which I'm going to use it in a minute. Is that correct or not? Yes? So let's go to problem number 29 in your book. And look at that problem first, because we have to use one of these. The three equations you want to concentrate for eccentric loading is this one, which is exactly like centric. Is that correct? No difference. But the only difference is in centric, sigma is equal to P critical over A. Is that correct or not? For eccentric, you have to use this. Is that correct? Which becomes the second formula. Yes or no? Which is that formula. So that is the secant. Because secant, because of this, because everything has a secant in it. Secant is 1 over cosine. Yes? Correct? Now, let's look at problem number 1029, which I'm going to do it on this board. So this is a column like this. Fixed, free, is 30 by 30 millimeter. So I'll go a little bit quicker. Hopefully I'll finish this on time. And then there is a load here. So first of all, for this problem, Ix and Iy are the same because it's square. So does not make any difference. However, they put the load here at, this is the centroid, they put the load P at 4 millimeter. So E, or eccentricity, is given equal to, 4 millimeter. The other data, this is all in your book. P is given 15 kilonewton. By the way, this is problem number 1029, similar to some of your homework, but it is for eccentric loading. Remember, eccentric loading is not as important as centric, because you will see when I go to the code, the whole thing is going to change. I only gave you 2 problems. Remember that problem 35, or see that 30 and 45, which is eccentric loading. 30 actually is very similar to 29. Is that correct or not? Yes? That's why I'm doing 29 for you. So that, and then what else is given? E is given equal to 70 G Pascal, which means this is an aluminum type column. And the length L of the column is given 0.6 meter or 600 millimeters, so it's a short column. And 2 things we want to calculate. Of course, sigma yield, I don't need it, but sigma yield is, for aluminum, is around 100, 110 megapascal. Is that correct or not? You can look it up in the table, correct? And then we want to calculate 2 things. We want to calculate the vertical displacement, because this is fixed. So as the result of that one, this may go like that. Everybody understand that, because it buckles, and it buckles like that. So in other words, P is here, and it buckles like that. This is Y max. For this problem, Y max is on top. Y max is not at the middle, because when we were driving it, Y max was at the middle. Remember that? So when we're driving this equation, I have it still here. For pin, the maximum was at the L over 2. Actually, here is different because of 2 things, because we're changing L effective. So what we are saying here, as I did, I don't have to do it again. If this is fixed free, since it's going to go like that, remember that is not like that. Is that correct or not? Since we are using K equal to 2, therefore maximum deformation is here, which is equal to that, similarity to that. Is that correct or not? So there we calculate here, here we calculate there, because this curve is exactly the same curve. Is that correct or not? So what I was saying, so be careful of what the difference between each problem is. The maximum deflection are in different location. In this one is obviously will be on top. Is that correct or not? As due to this phenomenon. So therefore, this is the Y max. So that's what they want to calculate here, which the formula is given. I don't have to worry about it. So formula is given there. So I'm going to use exactly what they have given me there. So I need the area first. So the area is 30 by 30. So therefore, it's 900 millimeter square, or equal to 900 times 10 to the power of minus 6 meters. It's advisable everything to be in meter square, because you want to use the Pascal. Pascal is Newton per meter. The only problem the student usually have is not the statica problem or not formula, because formula will be given. The only problem they have usually in this chapter, because of lack of practice, is the unit. They mix the unit together so many times. I have seen more than 50% of the class do not get the unit right. So be careful here. Then you calculate I, because here doesn't matter. Ix is equal to Iy, doesn't matter because it's square. Is that correct or not? So it is equal to 1/12 of, everybody can calculate that, 30 times 30 to the power of 3, yes or no? Correct? That's the cross section, 30 by 30. So you calculate that one, that becomes 67.5 times 10 to the power of 3 millimeter to the power of 4, or equal to 67.5 times 10 to the power of minus 9 meter, because we have to multiply or divide that by 10 to the power of 12. It is millimeter or meter to the power of 4. Yes or no? Correct? From plus 3 minus 12, so it becomes minus 9. Is that correct or not? We have done that in the past. Then the next thing we want to calculate is the, of course, the C is given, equal, E is given 4 millimeters, so that's we already know. L effective. L effective, since it is fixed free, it is KL. The K value is 2, correct? Remember from last time? Yes? fixed free is k equal to 2 because that's the worst scenario. So it's 2.2 times 0.6 is 1.2 meter. So the next thing is calculating LE over R. So I need R. Again, Rx equal to Ry equal to a square root of Ix over A or Iy because that's the same. If this was a rectangular shape, that's all I'm saying that. You have to calculate to see first which way it's buckled. Right? Here is a square, so it's simpler. However, the eccentricity is on this direction, so that you have to do A over X. So therefore, you calculate that one. You put all this number there. This one become equal to, let me put the number there. So it is I which is 67.5 times 10 to the power of minus 9 divided by area, which is 900 times 10 to the power of minus 6, eventually become 8.66 times 10 to the power of minus 3 meter, because this is meter to the power of 4, this is meter to the power of 2, so it becomes meter, square root of meter square is meter, then equal to 8.6 millimeter. So Rx and radius of gyration. Next is calculating our LE over R. LE over R now is equal to 1.2 meter or 1200 millimeter. Watch out for the unit because I have millimeters. I should convert that into millimeter or vice versa, meter over meter or millimeter over millimeter. Doesn't make any difference. This is the same. Millimeter over millimeter or 135 or 138.6. That is our slenderness ratio. The whole idea is all about slenderness ratio. Is that correct? The more slender it is, the more likely the system is going to buckle. This way, it doesn't matter. It buckles either way as far as the centric load is going. So that's what it is. Then, since it is eccentricity, so I have to use those formula. If it is centric, I calculate P critical. I'm done there. In eccentricity, this is what we get. Again, P critical is the same. P critical is equal to pi square E over LE over R square. So that is equal to 3.14 to the power of 2. E was given 70 G Pascal, 70 times 10 to the power of 9, divided by P critical multiplied, I need an A there. P critical is pi square EA divided by LE over R squared. I am using P critical, not sigma critical, so I need the A there. That's the formula. Be careful, the difference between P critical and P critical, the same thing here. I thought I used sigma. Sigma critical doesn't have an A, P critical has an A. Everybody understand? Yes, because sigma critical is P over A for centric loading. Is that correct? So therefore, that is what it is there. So you have to be very careful. So you put it there, multiply that by A become equal to, where's the number? 900 times 10 to the power of minus 6. And this is 70 divided by 138.6 to the power of 2. Eventually, P critical become equal to 32.3 or 4, let's say 3 times 10 to the power of 3 Newton, or equal to 32.3 kilonewton. So that become P critical, according to the formula that it was given to you. Now, the next question he's asking you to do, part A of the problem, is to calculate, that's why I put this on the board, to calculate Y max. Yes or no, right? To calculate Y max, all I have to do use the following formula. The following formula, look what you have there. I put the formula there, so it is your Y max equal to, as I said, it is very simple. You have to follow the formula is in front of you. It's in your handout. Will be given as a formula sheet to you. Everybody understand? Just use it, but do not make any mistake in the unit. Is that correct? E is how much? E is 4 times 10 to the power of minus 3 because it has to be in meter. multiplied by secant of pi, which is 3.14 divided by 2. Secant, the parentheses go there. Square root of p over p critical. How much p do we have? P is 15. And p critical is how much? P critical is 32.3. If it was centric, that would have been the factor of safety. Everybody understand? The factor of safety for centric is p over p critical, yes or no? Or p critical over p. Is that correct or not? Here we have eccentricity. Everybody understand that this scenario changes. That's why we have to be careful here what we are doing here. If it was centric, the rest of the problem is the same. All I have to do at this stage, if p was at the center, then I have the 32 versus p. Is that correct or not? Yes, that would have been my, here, change a little bit. Y max become like that. P is 15 divided by 32.3. Is that correct or not? Multiplied by L. L is how much? L is, was given, look at it. L is given, L effective, which is 1.2. Yes or no? Right.
Why are we multiplying by L instead of subtracting 1?
What?
Isn't that Y max?
No, that's the formula. P over P critical. I'm sorry. That's the other formula. I'm sorry. So that's right. Nothing else. That's right. Yeah, that's Y max. I went to the other second formula. For a while, I thought I'm the second part of the problem. Yes, so that's it. No, there's nothing there. Sorry. Minus 1. Yeah, of course, this is kilonewton and this is kilonewton, so it works. Is that correct? The unit works. So this is minus 1. No, I'm not finished yet. So that's right. I know that. I know that part of it. Because I was trying to put L over 2, which is the second formula. But second formula looks the same except it's L over 2. But what I put here, when you change this, actually this is equal to P over P, pi over 2, P over P critical. That's the same thing. You don't see it there. But that's how it works. Because P critical is, P critical is pi square E. If you change it, this formula changes to that format. Is that correct? But then, yes, here this has L over 2, the other one doesn't. Is that correct or not? Yes? Nevertheless, that's the formula. Agreed or not? Yes? Correct? So you do that. The only thing you have to be born here, this is in radian when you want to calculate 1 over cosine and you are using your calculator in the angle. Be sure this is radian. So change it to radian or change the radian into angle. Is that correct or not? So therefore, this become Y max become equal to that you do all those numbers together, 4 times 10 to the power of minus 3. This become secant of 1.069 minus 1. That's what I'm saying. How you calculate this one, be careful at that. This is 1 over cosine of 1.09, but 1.09 is in radian. It is not in degree, and many people make mistake there everywhere. Of course, if you put 1.9, 1.06 degree, that become 0.999. Everybody understands. It's near 1. Everybody see that. Cosine of 1 degree is near cosine 0, which is 1. Yes, correct? Don't do that. That is 1 radian. Is that correct or not? So please be careful what you are doing there. So that's all I'm saying. That the Y max become, after you calculate that correctly, Y max become 4.31 times 10 to the power of minus 3 meter, or equal to 4.31 millimeter. The second part of a question is this. The second part of a question is calculate sigma max. I think that, yeah, that's right. First calculate M max if you want, and then calculate sigma max. I can use this equation, or I can go directly to that. Because now that I have Y max, I don't have to go there. I can use it here. Everybody understand what I'm saying that? Yes? Since I have this, why should I use that equation? That equation puts 2 and 2 together. Everybody understand? In this equation, already we calculate Y max. Is that correct or not? And I have Y max. I have the E. I have the P. I have everything. I can calculate my sigma max that I can put on this column. So sigma max equal to, so write it down. It's very simple because we already have everything there. So we put P over A, which is 15 times 10 to the power of 3 divided by area 900 times 10 to the power of minus 6 plus P which is again 15 times 10 to the power of 3 multiplied by what? Multiplied by E plus Ym. Is that correct or not? Yes? So E is how much? E is 4 millimeter, and that is equal to 4.3. So it is 8 point, yeah, 8 point, whatever that is, 8.32. So therefore 8.32 times 10 to the power of minus 3 and multiplied by C. C is given for this problem. C was how much? C is 15 millimeter. So multiplied by 0.015 meter divided by I is given. I was 67.5 times 10 to the power of minus 9. Anyhow, you calculate all this sigma together, that sigma becomes 44.4 megapascal, which is much lower than sigma yield, which should be somewhere around 120 megapascal. So we are 1/3 there. Remember we were there, this scenario? So here is, I don't know, sigma yield, whatever for aluminum is. It depends what type of aluminum. Should be around 110, 120, around that area. And you are only at 44. So it is going to be like that. Okay? Now, let me not do what I did for the other class. For the other class, what I did, I went and tried to use this equation with the second problem in your handout. Look at the second problem in your handout. Unfortunately, because of this become a lengthy problem, I was not able to go through the code, which is much more important than that one. Let's first do the code, and if I have time, then I go and give you the essential part of that second handout. So in other words, I'm going to the third example in handout, which is very similar to you see these two problems actually exactly use the same two formulas. You see those two formulas sitting there, the second formula and the one, but only one warning. Again, going back to the scenario, if I give you P, you can put it in this equation, calculate sigma max, as I did it here. Is that correct or not? If the problem is in reverse, which is sometimes it is, sometimes they give you sigma max, and they ask you to calculate the value of P. If that's the case, this is not solvable, because there is a P here and there is a P there. Everybody understand that? And this is 1 over cosine. No way you can solve it by hand. Notice when I put the value of P here equal to 15, I was able to finish this problem. Did you see that? Yes? If the problem is reversed, let's say this, I want this to be less than 80 megapascal, because some problem are like that. Find the value, how much P I can put in this column. You cannot do it unless you go to the graph. Everybody understand that? The graph was this. You calculate this. On the graph, let's put it the graph. That's what I'm not going to do problem number 2, but that was the essential part of it. In the graph, you need two things. The graphs are, look, there are a bunch of curves going like that. Everybody see that? This side is L over R, or L effective over R. So you calculate your LE over R, which we didn't do it here, or we have to do it there. So you calculate your LE over R. You go to this point. Then you calculate your EC, two things you need. You need LE over R, and you need EC over R squared. Why? Because there is a E. If there is no E, there is no eccentricity, the whole thing evaporates. But if there is an E, which there is for this problem, E equal to 4 millimeter, then you go here to one of the curves, you go up here to particular curve which has EC over R. Let's say EC over R become 0.4. Let's say LE over R is 50. Actually, the second problem, practically, actually that was 0.3. For the second handout problem, if you calculate EC over R, become 0.299, something like that, which is 0.3. LE over R become equal to 49.95, which is 50, the second handout. So you go here to 50 unit, and then you go to the one that's nearer to that one. You go here, you read the value of P over A, and that way you calculate the P. Everybody understand that? That's approximate P. But then when you find the approximate P, then from there you put the P here, and if this, let's say the P end up for that problem, P end up to be, I recall, 650 kips. So I put 650 kips here, and I check it to see whether I get to sigma max. If I get lower, means I have a lower value. If I am above that, so I use the trial and error. This gives you an indication where to start. So because this is approximate, is that correct? So you don't know whether you should start at 10 kips or start at 1,000 kips. It is very wide variety, but the graph gives you approximately where you are. Is that correct or not? So for our problem, I recall even EC over R was 0.3 and LE over R is 50. Go there. You will see what I'm talking about. Go to the graph of the, not metric system. Go to the R system. You see there is two of them, two graphs. One are R system, one is metric system. Which one are you looking for? Yeah. You see, this is, yeah, that one, you know. The second problem is, this one is metric system. The one I'm giving this problem, let's say this is for foot and inch. This is for foot and kips type sort of thing. So this number is given. You have to go to the graph there. I recall we went there. What did you read for P over A? Something around 27.5, 28. Is that correct? Was you reading there? No, this one. Go 50, go up to point. Yeah, there, you come here. You see that? 20, 28, 29. Yes or no? Yes? Maybe a little bit higher, 28. 28 is here, correct?
Yeah.
Okay, so what you see for this, this is what you read. You did P over A equal to 28 KSI, and then whatever A with that problem was given, you calculate the P end up to 650 kips, and then when we put the trial and error, we end up P equal to actual value was 7, because this is very approximate. So actually, it was a little bit higher, as you noticed that. So it should be 28 something, that near 29. But nevertheless, the graph is a good indication where to start. The rest of it will be for prior error. Again, I'm repeating that. When sigma is given, you choose any value here. If the value is low, this bracket becomes much less than this. So you have to increase your P to the certain level. The two become equal. That's what we call it numerical method, or trial and error. Everybody can do that, but that's the repeat. That's why you have to be careful. Now, saying all of that, so the whole eccentric loading is this formula, and that formula, and that formula. That's all it is. It will be given in the handout to you. Yes?
Is it possible to use that form of
yes.
sigma to find P?
Yeah, but that's the same thing. Again, you cannot find Y max because Y max has the P. You see? It's not 1P, it's 2P. So when you do that, that's the same. This formula actually changes into that. Yes? It's very interesting to look at that formula. Let me, actually, now that I have time, I can explore this a little bit further with you. You see this one? Sigma max. You know what that is? P. It doesn't look like that. That's P over I, 1 plus EC over R squared. Yes or no? Plus that. What do you think this is? This is really the effect of buckling. If there is no buckling involved, look what this equation becomes. This equation becomes sigma max equal to P over A times 1 plus EC over R squared. Yes or no? If E equal to 0, sigma max equal to P over A, centric. Yes or no? If it is eccentric, there is the E there. Look what this formula becomes. The sigma max equal to P over A plus what? P times E, C over A R squared. What is PE? PE is no buckling, I'm talking. PE is M. What is AR squared? AR squared is sigma equals P over A, MC over I. You don't see that, but it is all there. You see, centric load is there, eccentric is load there, buckling is there. That you are, in other words, you are reducing your system by that much, which is the effect of that. If buckling goes away, this becomes equal to 1. Is that? The closer you have to the crushing, this number becomes closer to 1, everybody, and you get away with the LE over R larger and larger, that value become less than 1, so you are reducing your value of P. Is that correct or not? So let's say there was no buckling, this become equal to 1, and this formula becomes sigma max equal to P over A plus MC over I, the one that you were using in ME218. Yes or no? If there is no E, then EC over R squared become 0. It's a centric loading, sigma equal to P over A. So this is really what it is there, exactly everything, all the formula actually. Let's put it this way, fact, I don't have to tell you all the trick of future. You can never, ever design a rod under centric loading, sigma equal to P over A. It doesn't exist. That's the formula. I tell you that. Because you can never put the load at the center of a rod. Is that correct or not? That is impossible. Always the code tells you, okay, if you want to put a rod, you want to design a rod like that, always give yourself 10% of this width eccentricity. You have to do that. You have no column. If it is a compressive column, that equation comes into the picture. So every time you see in the code, it's P over A. This is theory, is P over A. This is the actual one. Is that still this is theory? You will see that in a minute. I'm going to change that one too. Okay. But, so it is going to be every item which is designed for the compressive member should be checked for buckling, except when LE over R is very short. Is that understood? Yes or no? So therefore, that is the system. This equation appear in everywhere. Now, we have another problem, which we are going to discuss it now. Nevertheless, this was 3 equations in one. Centric, eccentricity, plus the buckling effect, which effectively reduces, because sigma max instead of being 36 or 42 or whatever is given, we come 20, 19, depend on the LE over R, because that will appear here and here. This is eccentricity factor, and this is the buckling factor, both of them there. This part is eccentricity, this part is the buckling factor. But that is how the formula works, and that is the result. You can do that. Now, the real problem. The real problem is this. Okay, we have now 2 formulas that we use there. One for eccentric loading, one for centric loading. And now we come to this. So this is the design. This is actual design now, based on AISC code. And by the way, there is one page I gave you in the handout to you, so you can't to throw that page away. So in the handout, show me your handout, guys. Not the last hand, not the exam handout. I'm talking about the class handout. Look at the page that it says code. This one. Okay, this one, which I used last time I teach this course. See that code? Zup. Gone. New one comes. So throw that one out. Okay. Now, I tell you this, because last time we were teaching the Hibbeler book. The Hibbeler book was using the old code. The old code existed there. Now the new book, they changed it to the new code, which is very similar. It's really the same, except now they become a little bit more conservative. And I'll tell you what's the difference between the two. Is that correct? So don't use that one. Use the one in the, don't use that one. Cross it out, please. I don't want you to get the no, cross that one out or throw it out. Just cross it, okay? Because we are only doing the still design. We are going to still design, so I'm going to give you the code that you see it in your book, which is a more recent one, which is both of them the same with the difference on 10, not 10% even, 3 or 4% different in some area, not all the area. For centric loading, actually exactly the same. For eccentric loading, which is more difficult to handle, they reduce the amount of load by another 3 or 4% based on the empirical formula or the test. So what happened here, guys, is this. That if let's first of all, this is designed based on the code. Let's go to centric first. So let's do the centric loading. So we are not talking about eccentric loading. Load is centric. The cross section could be either square or rectangular or I or W. Is that correct? Or still is going to buckle about which axis? We don't know until we put everything together. So the question is, you have to calculate LE over R. For LE over R is large, it's going to buckle about that axis. Is that correct? Which again, I'm repeating myself. It is the area is in it in the form of R. L is in it in the form of length, and LE, which is effective length, or K factor is there. Is that correct? Which covers the boundary condition. So you calculate LE over R for your column. Then this is the formula. P critical was equal to pi squared E. Notice the difference between P critical and, This was P critical, or here I'm putting sigma critical now. Now, this is P critical, which has A. Sigma critical is P critical over A, so I have to drop the A out. So LE over R squared. Is that correct or not? This is sigma critical, that was P critical. Both the same for centric and eccentric load. Okay, so that graph, as we saw it earlier in the last week lecture, LE over R versus sigma give us a curve like that. And of course, everybody agreed that this curve should not go beyond sigma yield. Okay. This is the theory, yes? So if I make a column very short, I should get an answer here. Is that correct? If I make a column very long, I should get all my answer here. That's what I was telling you the other time, that when I was a student, people were testing column. Still, if you go to some university to do the research work, they are doing the testing column to find out what's going on, because nobody can exactly figure out what is going on because of the following. So anytime since then, and since the beginning of this development of this theory, that anytime they put a long column or LE over R around this area, the result of the test and the result of the Euler formula are very close to each other. In other words, the Euler formula is good. Is that correct? That theory is good up to certain level. So you come here, somewhere around here, suddenly doesn't follow this curve anymore. It goes wide here and then become a little bit flat. Everybody understand? It means to certain level, which I'm going to call it CC, up to that point, this is the result of test. It's not the result of theory. I make here is the formula I have. I make a column, this size, this length, with this LE over I. I test it. Formula tells me I should get this much P, and I get different P. Everybody understand that? When I plot it, this is the result of plot. This side works, this side doesn't. Is that understood? Okay? So for this side, where is this limit? That limit, this curve depends on different material, different E, different sigma yield. Everybody understand that? Therefore, they calculate, this is the code now. So you want to write the code. The code says calculate the CC. If you look at the old handout that I just asked you to cross it, they gave a different formula. Now they give you a new formula. The new formula is 4.71 E divided by sigma yield. In other words, this CC depends on the type of material, depends on the modulus of elasticity, and depend on the sigma yield. So if you are using high strength steel, CC will be different than, let's say, ASTM 836. Because ASTM 836, E is 29,000 KSI, and sigma yield is 36 KSI. Everybody understand that? If you use high strength steel, E is still 29, maybe sigma yield is 42 KSI. Everybody understand? Then value of CC changes, because when they test different material, they see different result. That's what they come up with. Is that correct or not? The value of that. Now, if your LE over R happen to be in this area, larger than CC, you are okay with Euler formula, yes or no? So this is what we do. If, this is the code again, if your LE over R, your LE over R of your column is larger than this value of CC, means you are in this long range region, anywhere in between. Of course, you don't go that far. You are always staying here. Is that correct? Because this is impractical. Yes? So you are here, then you use the following. You calculate sigma Euler. We don't call it sigma critical. We call it sigma Euler, not sigma. So they changed that to sigma E, because that's the Euler equation, equal to pi square E over LE over R. In the previous code, they said, okay, divide that by factor of safety of 1.92. Recall that. Now they said do the following, which is the same result, exactly the same result. They said use your sigma critical as 0.877 of sigma E first. This is in the handout. It's very simple. You can follow the rule. You just read the handout that I gave you, part of a final exam. Sigma critical. In other words, don't use 100% of that. Only use how many percent of that? Only 87. That's all they are doing. They are reducing it. Is that correct or not? And then use the factor of safety of 1.67. So this is the new code. That's what it says. It's acceptable. Now, on the old handout that I gave you, actually, scenario is exactly the same. I said use this one and use the factor of safety of 1.92. Actually, if you divide this by this number, that's 1.92. Is that correct or not? Yeah. So that's the same, no changes. However, the second part will change. Don't mix the two together. Just cross out the other one. If somebody interested to know, the both old one and this one, they're all giving you exactly the same thing. So you are here, you are using Euler, but you are only using 87% of that. Is that correct? With a factor of safety of 1.6, or you can use this number and factor of safety of 1.92, exactly the same, because this divided by 0.877 is factor of safety of 1.92. If you look at the handout that I just asked you, cross it, that's exactly what it says. Is that correct or not? Yes? However, when things get on this side, we have no theory, because this does not for you. Now, what the people are doing, those who are doing research, some of you may want to do this if you want to do a project in future. I don't know whether we have the equipment for the buckling here. You can start buckling aluminum column or thing and come up with some sort of project out of it. Everybody understand for your final project. This would be idea. Anyhow, so then people are trying to put a parabola here. They put the E function here, the different function, because everybody tries to come up with some sort of formula, and none of them yet has come to the conclusion that we cannot predict it. In other words, we cannot predict the result of the test into a formula, exactly as I said for the other class that everybody laughed. We cannot predict what the stock market is going to do tomorrow. Can anybody predict that? Of course, there are 1,000 people or 10 million of people sitting in New York, and they are trying to, if you have money, of course, many of you don't, not yet. Not yet, I said I will. So if you have money, they are after you to sell their formula to you, but their formula is as good as my guesses, which is 50-50. Tomorrow, stock market either goes up or down. So their formula, they are telling you, I don't know whether they call you your parent or yourself every day, they call you, you want to use my formula to get rich, or phony. Everybody understand? Not phony. They have some formula. Their formula doesn't work. Here is the same. If that formula worked, they didn't need your money. They would already become billionaires. So why they are after your money to do it? They want you to take the risk. Is that correct or not? Yes. Therefore, this is the same thing. If one of you guys come up with a formula and tell me why this column behaving like this, then you get rich. Is that correct or not? Yes. So find it out, but you have to do some research work. Is that correct or not? Now, since this is not applied, so let's go to the second part. If this was for what? This was for long column. So if you see you are there short, or we call it short or intermediate. This is how they define the column. This is intermediate column. This is the short column. This is the long column. This is on the category of the long, which Euler formula works. We use a factor of safety of this and that together, which is 1.92, or this much of sigma E with a factor of safety of that. Now, if your LE over R of your column is less than CC, the Euler is not good. Is that correct or not? So Euler is way off of that. And again, for different material, different length, different cross-section, different sigma, different E, this is behave differently. Nobody can put all of them together, come up with a formula there, not yet. They are suggested, many of them in the literature, but it not. Then in that case, you do the following. Sigma E is the same. Sigma E still is pi squared E over LE over R, so the same thing for both of them. Then you use sigma critical equal to 0.658 to the power of sigma yield over sigma E, which is the Euler, which is larger than 1. So therefore, when this is larger than 1, this becomes smaller. So when it's 0.658, let's say that become to the power of 2, it becomes 0.36. So it becomes much smaller. Everybody understand that? Than 1. And then multiplied by sigma yield. So sigma yield is being reduced by 30%, 40%, 50%, 60%, depends what the ratio is between the sigma yield and sigma E. Everybody see what I'm talking about? Yes? At the limit of crushing, when you are near the crushing, look what happened. Near the crushing, this sigma yield over sigma yield become equal to near 1. So you are using a factor of safety of 1.67. Everybody understands sigma critical equal to still this much of that. Is that correct or not? So you are using only 66% of sigma yield, not total of that. Everybody understands that. But it still is there. And then you use a factor of safety. This is for standard for 1.67. What they are trying to make this very close to the crushing factor of safety, which is 1.67. So they are using the same factor of safety for everything. Is that correct? By modifying the original sigma, not the factor of safety. In previous code, they will give you different factor of safety for different scenario. That's the only difference. This time, they are using the same, this one, and for crushing, all of them, factor of safety is 1.63 or 5 over 3. I want you to understand. 5 over 3 is a factor of safety for a centric loading. And therefore, they use the same thing for all of them. But instead of modifying the factor of safety, if you go to the old code, you change your factor of safety, not the formula. Here, the new code, they change your sigma critical, but you keep the same factor of safety for all 3 cases together, which is P over A, eccentric, and the buckling, all 3 together. But nevertheless, your stresses are going to be adjusted. Notice the stresses become smaller and smaller because this is less than, this becomes 2 to 1. Everybody understand? If sigma Euler is 1/2 of sigma yield, this becomes 2. Yes or no? This becomes 0.6 to the power of 2 is how much? Is 0.36. You see, you're only using 36% of sigma yield because you are afraid of the buckling. Yes? If sigma E becomes closer to sigma yield, this becomes 1, so you are using 66% of the sigma yield for the yield for now. Everybody see that? That depends on that value, correct? So let's do example now. Let's go to example. This is very simple. I didn't finish that. This was for centric loading. The main part is remaining. I'm ahead of myself. I don't know. This is centric loading. Everybody understand that. So either you use this formula or that's your result. Look. Anybody has the handout that I gave you with the final? It's here. I can see it here. Can I use this? All of this. This is the handout you will get during the final as well. Everybody understand this is the one? Yes. Okay. Look here. All of this information is here. That's all you have to read. There is nothing more there. Everybody understand? But it looks long. But it's all here. Everybody see that? All that 3 formula that I'm putting here, and this one. This is all about the buckling with the design. So don't be afraid of it. It is there. You want to take a look at it, take a look at that one. Now we get to the eccentric loading. What do we do? This was all for code centric. Everybody see that? I put it here. You need 2 equations. This one, of course, is obvious. You need this, and you need that. Is that correct or not? Yes? Correct? All right. Now let's go to eccentric loading. In the eccentric loading, this is what we do. Okay. In eccentric loading, using the code, which is the subject of last 4 homework. Notice this 4 homework. This is theoretical formula, Euler equation, and all this for centric. This is theoretical formula with eccentric, which I put earlier in the class there. Is that correct? And these are the code. All of them are code design based on what I'm talking now. Is that correct or not? Which is the real one. So eccentric loading, now this is what we do. First, step 1, find sigma allowable. Because notice here I said factor of safety, but what I forgot to put here, everybody see that the factor of safety is 1.6. So sigma allowable become equal to sigma critical, either this equation or that equation, either that or that, divided by factor of safety, which is the same, 1.67. So that's the goal, to reach to the sigma allowable, and from sigma allowable, calculate the P allowable. So that was the goal. Here, find sigma allowable centric. So it doesn't matter. Okay, so it doesn't matter whether the load is eccentric or not. You just put the load at the center of the column first. Is that correct? And then calculate. In other words, you have to go through first. Doesn't matter whether it is centric or it is eccentric. So step one, so find sigma allowable based on, write it up, based on load on centroid. No or centric scenario, which is the same thing. You do that. Then use the following. Step two, there are two methods suggested. Both of them are acceptable or a little bit different. One is more conservative than the other one. You can use either of that one. One is the allowable stress method. Allowable stress formula, which is the following. After going through all of that, they said, okay, forget about that. Find this sigma allowable. This sigma allowable is much less than sigma yield. Everybody understand that. Sigma yield is 36. Depends how much buckling affects your problem. It could be 20 KSI, it could be 18 KSI, it could be 12 KSI. Depends on how much LE over. The larger the LE over R, the less is the sigma. Is that correct or not? We saw that in our formula. Therefore, you calculate that. Then you say, okay, I have a stress due to the P over A, and I have a stress due to MC over I, exactly like what we did in ME218. Is that correct or not? Yes? And in ME218, we always said P over A plus MC over I should be less than or equal to sigma yield. Is that correct or not? Stress due. But here you don't have to say sigma yield. You have to say this sigma allowable. Everybody understand that because factor of safety is there, everything is there. So less than sigma allowable. So if you use in the formula, I think 2 or 3 of your problem, they ask you to use this formula, which it calls allowable stress method. Is that correct? Is that understood? Yes or no? Correct? Then some people later on, when we're doing this research, they said, okay, why should we do that? You see, this is very interesting. This is the stress due to the centric loading, which may cause the buckling. This is the stress due to what? We are not considering buckling about. This is the stress due to the bending action. And we are adding there, let's say this is 4 KSI and this is 8 KSI, and this should be less than 12 KSI, which is much lower than sigma bending. Is that correct or not? Because this is due to the buckling. So this is sigma allowable, write it down. This is sigma allowable due to buckling because we consider buckling phenomena to get there. So they say this is too conservative. Let's do it this way, and which is a better way to doing it. They did it like that. They divide P over A by sigma allowable buckling. Notice if you divide both sides by sigma allowable buckling, this is buckling. Buckling plus MC over I divided by sigma allowable buckling should be less than or equal to 1. But now we change that from buckling to bending, because these are two different phenomena. See, if I'm finding a stress due to this and a stress to you, why do I have to use sigma allowable buckling for both of them? Everybody understand that. If this formula says this divided by C allowable buckling, this divided by C allowable buckling should be less than 1, yes or no? But they said no, change that to sigma allowable, instead of buckling, change it to bending, because this is the stress due to the bending. By saying that, so we get a little bit, a 10% or 5% between, depending on the column, 5 to 10%, a better result. Is that correct? So some people uses this one, most people actually use this one. So this is called interaction. So interaction formula. So it means do not, actually it's reverse, do not interact this with that one. Separate this one, this is the stress, and this is sigma allowable. So this is the stress. Usually sigma allowable bending is much larger than sigma allowable of buckling. Therefore, you get a little bit better result. It's less conservative. So that's the code. So still part 1 is the same, part 2 is little change. So we have now 10 minutes to go through an example, which is very good. So let's do one of the example in your handout. So let's go to the handout problem. You see how I use both method, or use one method or two other methods. They use both of them. So let's use that one. Okay, let's see what's the difference between two. Let's look the handout problem. So in other handout, let's erase all of that. So I don't want, just put the picture, if you have your handout from the final, pick up that one, because that's the better, or if you have the book with you, or let's leave some of this on the board so you see what happened here. Let's go to the problem number 3 on your handout that I gave you, which is actually from your book. If you look at it, that's the same problem as 1066. Actually, you see that? This is the same problem at 1066 in your book. So this is the following, this is the example. So please write it down. This is a W250 80. Yeah, this is the one I did. W250 80. Sigma yield, this is highest strength. Usually sigma yield is 250 megapascal. This is a highest strength steel column. So they use sigma yield equal to 345 megapascal. And of course, E, modulus of elasticity, is 200 G Pascal, standard one. The effective length of this column, everybody knows what the L means. We are consider boundary condition, etc., etc. L effective, for simplicity, is given equal to 9 meters. And everybody knows that by saying that if I put here an X here and a Y here, this column is going to buckle about the Y-axis. We know that from experience we have from static and ME218. Yes or no? Yeah. Therefore, it's not a good column to design. Therefore, what did they do? They put here a plate here and a plate there, and thickness of that plate is given to be 10 millimeter thick, 10 millimeter, and the height is not given because we covered the height. In other words, we make it a box. When you look from outside, it looks like a square. Is that correct? This is the entire column. This is the cross section. Some people still have a problem with this one. This is what we did, guys. This is the column. I'm just saying that because I have seen people do that. Then you put a plate here all the way down, a plate on the other side. From outside, it's plate, plate, plate. Everybody see that. You don't see anything. It looks like a square column. But inside is that. Is that correct or not? Now, which way is buckle? We don't know. Is that correct or not? Yes, so we have everything there. The question is first, find the P allowable centric. So this is the question we want to allow. P allowable centric for this column. Okay? And then I add something. I think the book also goes there, stop there. But then I said I added something to it which is not in the book. So let's say that we have an eccentricity of E equal to 40 millimeter, part 2. This is part A, which is in the book. Part B, I'm going to add it myself to that. Let's say we have an eccentricity E equal to 40 millimeter here. This way, this is E. So I'm not putting it this way, I put it that way there. I think that's what I said. I don't know, I have to look back. On the web, it says, yeah, that's correct. On the web, this is the web. Is that correct? That way or this way doesn't make any difference. Yes, sir. This is not in the book. So if I have a load, put my load there at point E, and E is given equal to 40 millimeter, then calculate P. Now, what P can I put here? So this is different from centric. Yes or no? Yes? However, part 1 is the same. I said eccentric and centric, we have to go through that anyway. Yes or no? Correct? So let's calculate what our scenario is. L effective is given. I need the R in order to calculate LE over R. I don't know whether I should go X or I should go Y. This is the X. This is the Y. Is that correct or not? Let's go a little bit quickly because otherwise we cannot finish this problem. The A is equal to 10,200 millimeter square. That's A of this profile. The A of this two is 10. I don't know how much the height is. The height depends on the height of the beam. Is that correct or not? We get that in a minute. So, or the D, this D from here to here from the table is 254 millimeter. The height of this plate, therefore, is 250. The D of the flange or this side is this from here to here is 254 or also 254 millimeter. Notice this is this side, almost the same. IX is given for the profile. IX from the table, 126 times 10 to the power of 6 millimeter to the power of 4. IY, I can convert it to the meter, is equal to less 42.9 times. That's what is given. Okay? Which way is going to buckle? If I want to go to the centric, first of all, I have to calculate my LE over R. No what problem, whether it's a code or uncode or whatever it is, everything depends on LE over R and which way is buckle. Is that correct? That is a standard. Yes, I have to calculate. Which way? I don't know until I calculate what, if there was no plate here, obviously, again, for the last time, it would buckle about the y. Why? I don't know that. So let's calculate nu I. You see, this requires parallel axis theory. Nu Ix is equal to 2ix, or 1ix, because 126 times 10 to the power of 6 plus 2I of the plate. Yes or no? I of the plate is with respect to this axis. Yes or no? Do I need parallel axis theory? No, of course not. 112 of base. What is the base? Base is 10 millimeter times height. Height is 200. Oh, this was 257. I'm sorry. This is 257. This is 254. I said it 257, but I wrote it 2. This is 254, and this is 257. Sorry, my mistake there. I put it down. Then times 257 divided by 257 to the power of 3. That's all we need. 112 of base times height cubic. Yes or no? Correct. So this is the nu Ix. So the nu Ix become equal to 154.3 times 10 to the power of 6 millimeter to, in other words, increase a little bit because there is only 2 plates there. Yes or no? However, Iy is going to increase a lot more. So Iy is equal to nu Iy. Nu Iy equal, this is all the practice of I, is equal to old Iy, which is this one. So it is 42.9 times 10 to the power of 6. Is that correct or not? Yes? Plus what? Plus parallel axis theory I need, because now I have to find this I of the y prime and use AD squared, yes or no? Because it needs the parallel axis, yes or no? So therefore, plus 2, I put it in maroon that you see that's the color. So 112 of base is 257 times 10 to the power of 3, which is relatively very small, plus what? Plus A times D squared, yes or no? The A times D squared, A is what? 257 times 10, that's the area, multiplied by D. What do I need D? I need half of 254, add to half of, because this goes on top of that. Is that correct? Or I didn't write that correctly. That goes on top of that. Is that correct or not? Yes? You see where the plate ends. So I need half of 254, which is 177, yes or no? Plus half of thickness of the plate, which is 5. So therefore, put it there. A little bit problem there. We have to watch out. 254 divided by 2 plus 5 millimeter, half of that to the power of 2, and then you use the bracket. So in other words, you need parallel axis theory, and therefore the nu Iy become 132.5 times 10 to the power of 6. Which one is buckle now? This is the whole thing. Still buckle about the y. If I make much bigger plate, maybe it would reach that equal. Is that correct? Still buckle about the y. Then I need r, ry. Now this is the mistake that some people do. The ry is not ry in there because in the text they give you rx and ry. But that is not for this profile. That's only for 250. You cannot use that one. Is that correct? You have to recalculate your rx and because you've changed your profile. That's the whole thing. So ri equal to square root of iy. I'm going to running out of time, so I'm going to go faster. Iy divided by what? By area. But area also has changed. Everybody understand that. So you have to put area of the area of the profile plus 2 area of the plate. Is that correct or not? Because you have the plate there. So that you calculating that way. So R become equal to 92.9 millimeter. And then LE over R, let's go faster. LE over R become equal to 9,000 millimeter divided by 92.9 millimeter, or you go meter over meter, either way. So it is become 96.8. This does not define anything yet. That defined my LE over R. Now I have to this equation to see where is my CC is. Above or below, which formula to use. Is that correct or not? If my LE over R is larger than CC, then I have to use this formula, yes or no? If it is less than CC, then I use this formula, correct or not? So the next object is going through the code. Now this part is in the code, it's given in your handout. So you go to that handout. This is what you have to do for every homework. The rest of it is given there. Follow there. That whatever is written there. Is that correct? You don't remember anything. So you calculate that. CC was equal to what? CC was 4.75 E over sigma yield. E is given, sigma yield is given. You see that? You just be careful there. So that one become equal to one, for this problem, become 113.4 is therefore my LE over R is, which is 196, is less than CC. Is that correct or not? Yes? So where are we? We are not here. We are there. Is that correct or not? So what was the formula? The formula, I'll almost erase it here. Yes or no? That's the formula there. But I can do it again. So I have to calculate sigma Euler first. The sigma Euler, we did it before, is equal to pi square E over LE over R to the power. Now, what's LE over R? I have to calculate the R. You see, we did it here. LE over R is 96.8. So therefore, you put all of that there. Sigma E become equal to 210 megapascal. Because LE over R is 96, pi is pi, E is given there. So everything is there. So you calculate 230 versus what? Versus 345. Everybody see what I'm talking about. This is for buckling. This is for crushing. Everybody understand that. So you reduce it. That's what it is. And then you said, OK, formula. What formula did we have there? The formula that we have there, sigma. Remember sigma critical? We said 0.658. Is that correct or not? To the power of 345 divided by 2 times. Sigma yield over sigma Euler. It is there, but you don't see it there. It is there. Is that correct or not? Yes? Correct? Multiplied by sigma yield. This was the formula. 0.65 sigma yield over sigma Euler multiplied by, I said this is always less than 1. Is that correct or not? When you calculate that one, this become, look, this become almost 1.5. Is that correct or not? Then you twist to the power of 1.5, which is become a smaller 0.5. So you can figure out that. This become 104 megapascal. Notice, again, reducing. So then that is, and P allowable become equal to 104 divided by, I'm sorry. This is No, I have, no, this not become 104. I don't have that number there. They have one number there. Then you calculate that one. Then you say sigma allowable. Well, how do they do it? I did it myself here separately. I should use my own. So let's do that. What did you find out? 173. Okay, now then you say, okay, sigma allowable or P allowable. So first of all, sigma P critical become equal to 173 times area. And then you calculate sigma allowable, which is P critical over 1.67. So you calculate all of that. And P allowable end up to 1596 kilonewton. So you divide that by factor of safety. This is if it was centric, yes? If it was eccentric, what do? I have run over time, but let me finish that. This was if it was centric, yes? If it is eccentric, I have to use either interaction formula or a stress allowable formula. In the stress allowable formula, let's use the stress allowable formula. That gives you a lower than it is that. Then you say sigma allowable, oh, this is P allowable somewhere. What did you find that here was, okay, let's calculate, there's something here missing. See, when I miss something here, I get the sigma allowable is also equal to 173 divided by area. Is that correct or not? Yes, I missed one step there. Is that correct or not? And then P allowable, of course, it becomes sigma times A, so this is P critical, or is it sigma critical? That's sigma critical. That's what yeah, that's it. See, when I rush it, this is what happens. This is in case. This is in megapascal, yes or no? Correct? So anyhow, sigma allowable, write it down. Sigma allowable, after you use the factor of safety, you can calculate that yourself. P allowable become 1596 kilonewton, which is use a factor of safety of 1.67. And when you put it in that equation, this is finally you did. You say P over A plus MC over I now should be less than or equal to sigma allowable. Sigma allowable is 173 divided by 0.6. So calculate that one. Give me, if that is 173 is correct, sigma allowable 173 divided by 1.6, which should be how much? 103. 103, okay. So that's 103 megapascal. So you say this should be less than or equal to megapascal, and then you calculate P. This is your P, and this is your P times E. That's it. So you calculate P or use the other formula. Sorry for that one. Other side. It's just so much to talk in so little time. I'm sorry. I have to rush it a little bit. But don't worry about it. This is all in your handout. Try to do your handout. You need one more thing to do, and that's this one. I'm sorry for that, too.